Limits of infinite sequences. A sequence that does not have a last term is called an infinite sequence. Infinite means that it goes on forever. So that's the case that we're looking at here. Consider this sequence: 1/2, 1/4, 1/8, 1/16, and so on. Okay, now if you look really close at this sequence, you're going to realize that what we're looking at is a geometric sequence. Our starting term is going to be 1/2, and all we're really going to do is continue to multiply by 1/2 as you move down the line. But you can summarize it like this. We could say that any term in the sequence would actually just be 1/2 to the nth power. The first term is going to be 1/2 to the first power. The second term is going to be 1/2 to the second power, and so on. So we can summarize it that way. Okay, but what we want to look at here is what happens as you continue out into that sequence for a really long time. What happens when your n gets really big, when you're moving really far out into that sequence? Okay, so if we were to take 1/2 and start raising it to higher and higher powers, what actually happens to the value of that term? It starts off at 1/2, it then becomes 1/4, which is half of that size. Then half of that size is 1/8, and so on as you go down the line. So we should see that as you go further down the line here, your value is going to get smaller and smaller and smaller. So what does that really mean that it's doing? So let's go ahead and take a look at the 10th term. Okay, so I'm going to skip ahead here by using the calculator. I'm going to take 1/2 and raise it to the 10th power, which is the same thing as 0.5. Okay, let me raise that to the 10th. And I get that number, which looks sort of odd in its structure. It isn't a fraction as we're seeing here. But what it's indicating here is that this number is actually really small. Okay, the scientific notation means that the real form of the number would move that decimal 4 spots to the front. Okay, so the 10th term is actually going to be equal to about 0.000976. The 100th term is going to look like that, at least in scientific notation. Okay, so the true form of this number, though, would be to take that decimal and move it to the front 31 times, which I'm not going to write out here. So I'm going to leave it in scientific notation, which you can also write this way. It's 7.89 times 10 to the negative 31. But what it means in its true form is that you're going to have 30 zeros in front of that 7. You can have a decimal and you can have 30 zeros in front of that 7. Which means that as we go further out, not only are these numbers shrinking and we describe them as that getting smaller, but they're getting incredibly close to 0. The value of each term as you move down that sequence is going to tend towards 0. But it never actually gets there, which is kind of interesting, because every term that you take, you're still getting back half of that term, which means you can't ever actually be at 0. You can get very, very close to it, but you're always going to have half of the previous term. All right, next what I would like to do is create what would sort of be like a scatter plot that will help us see how these terms are getting closer and closer to 0. Okay, so what I have set up here, along the x-axis will be my term number. Okay, so that'll be my first term, this will be my second, and so on. Okay, for my y-axis, I got up at the top here 1/2 because our sequence actually starts at 1/2, and as you go through the terms, they're actually going to get smaller. Okay, so I'm going to start at 1/2. The very first term is here. Okay, T1 is at 1/2. T2 is 1/4. It's half of that number, which is going to be here. So that would be 1/4. We could go ahead and label that half of 1/2. Our third term is going to be 1/8, which is half of that number. So that'll bring you down to here. And you can see that we're getting closer to the x-axis, which is getting closer to 0. Okay, but when you go to the fourth term, we're going to get 1/16. Or we can just describe it as you're going to get half of that term. So you're going to be here. And after that, you're going to get half of this term, which is going to put you about there. And then you're going to get half of that, and half of that, and we get to a point that I probably can't even plot the dots correctly. But the idea here is that you're always keeping half of it. So as you move along the sequence, you're getting back less every time, and you're getting closer and closer to 0. At some point, it really just looks like it is 0. So here's how we summarize our observations. we say that the limit as n approaches infinity of 1/2 to the nth power is equal to 0. We do say that it equals 0, even though the sequence never actually gets there, because what we're talking about now is what's called a limit. This is what the sequence tends to do. Okay, that's what the limit means. It's getting closer to something, even though it might not actually be there. Okay, the limit as n approaches infinity, so as n is getting bigger and bigger and bigger, for this rule is going to give us answers that are getting closer and closer to 0. And in case I didn't say it exactly as I should, you should read this as the limit of 1/2 to the nth power as n approaches infinity is 0. For example 1, we're going to make a graph of the first 6 terms and evaluate the limit of a sequence that would be generated by using that rule. To make things a little bit easier, I'm going to use a calculator to generate the sequence for me. That way I don't need to go through and do each of the terms individually. Okay, but I am going to be evaluating the first term, the second, the third, fourth, fifth, and sixth. Okay, so in other words, I need to take those numbers and plug them into that. But I'm going to let the calculator do all the work for me. All right, so here's how I'm going to do it. In my function setting, I'm going to type this in, but instead of n's, I'm going to be using x's. Okay, so I got 1 plus, we'll go ahead and set up a fraction. We got -1 raised to the x power divided by x. Okay, and of course, if I hit graph, I get a picture of it, but that's not really what I'm looking for because I just want values at those select integer numbers 1, 2, 3, 4, 5, and 6. Okay, so I'm going to get those values from the table instead. But before I do that, I'm going to set up the table. So I'm going to go to my table setup. I'm going to tell the calculator to start the table at 1 because I don't really need to see a 0 value. And after that, I'm going to change the setting so that it tells me the numbers in order. Okay, so I'm going to go to the next part here, which is the change in your table, and I'm going to set that for 1. That way, when I go to the table, I'm going to see x equals 1 first, and immediately after that, I'll get x equals 2 and then 3. Okay, so go to the table, and these are the values that we get. Okay, so graphing that, let's see here. All right, so I should probably look at these fractions and get a good idea what they are as decimals because when I graph them, it's going to be easier to do that than using fractional forms. Okay, so at 1, I'm getting 0. Okay, so that's pretty straightforward. In fact, I'll go ahead and just plot that point. At 1, I'm getting 0. At 2, I'm getting 3/2. That would be the same thing as 1.5. At 3, I'm getting 2/3, which is 0.66. At 4, I'm getting 5/4, which is 1.25. At 5, I'm getting 4/5, which is 0.8. And then last, 7/6. Okay, let's check that one out. 7 divided by 6 is going to give us 1.16. All right, so it appears as though the numbers, they kind of bounce around a little bit, right? Goes up, goes down, goes up, goes down, goes back up. But hanging pretty close to around like 1. All right, so for my y-axis, we're going to go ahead and make that 1. Let's call that 2. And of course, that would be 0.5, and that's 1.5. And 0. All right, so we already have the first plotted. At 2, we're going to get 1.5, which will be here. At 3, we're getting 0.66. We're going to have to estimate a little bit. About 2/3 of that direction, maybe about here, should be pretty good. 5/4, 1.25. That'll be right there in the middle of those two. All right, 0.8, getting a little bit closer to the 1 than that is. It's about here. And then you've got 1.16, which is also closer to 1 than 0.8 is, but on the top side that we have there. So we've got these dots that are bouncing back and forth, right? They go up, they go down, they go up, they go down, but they're doing less every time. In fact, if we continue this out, if we continue it out, you're going to notice they're just going to keep getting closer and closer to 1. Okay, never actually becomes 1, but these dots appear to be approaching that line right there. All right, so we got our first 6 terms graphed, and we're asked to evaluate the limit. So we would write this. We would say that the limit as n approaches infinity, we draw that a little bit better. All right, the limit as n approaches infinity of this, you just have to copy it, is equal to whatever the dots appear to be going towards, which is 1. The limit as n goes to infinity of that expression is equal to 1. All right, suppose that you're interested in evaluating the limit of an infinite sequence, but you don't want to plot a lot of points and look at graphs for these things. There's a couple different options that you can take with them. The first is just to substitute in a very, very large number for n and see what that turns out to be. Now, what is a large number? Sometimes kind of depends on problem to problem. Sometimes 10 can be a large value for n. Sometimes it's 100, sometimes it's 1,000, and so on. Okay, but we imagine what would happen to the expression if we put a big number in for n, okay? And what would happen if we put an even bigger number in for n? And based off of that, we can sometimes come to the conclusion of what the limit would be. Take this, for example, the cosine of 1 over n. As you plug in larger and larger values for n, the fraction that we have there, 1 over n, is going to become smaller. The numerator is stuck at 1. If you keep increasing the denominator, you're getting closer and closer to 0, like going from 1/2 to 1/3 to 1/4 to 1/5. You're getting less and less and less. So on its own, the fraction that we have right there, the limit of that as n goes to infinity is essentially 0. Okay, now we still have a little bit more here. We're asked, what is the cosine of 1 over n as n gets bigger? Well, we can go ahead and think of this as the cosine of 0, because this itself is getting close to 0. And the cosine of 0 is equal to 1. All right, for the second, we're going to be taking 0.99, which is a little bit less than 1, and that's important. We're going to be taking 0.99, and we're going to keep raising it to a higher and higher power. Okay, now normally, when you take something and you raise it to a power, you get back something larger in return, because you're multiplying it by itself. Then you multiply it by itself again, and you get back more and more and more. But this number, 0.99, is actually just a little bit less than 1, okay? It's 1% less than 1. You can think of it as 99%. So every time you multiply this by itself, which you're going to keep doing more and more as n gets bigger, you're only getting back 99% of the number that you had before it, okay? So you're getting back less every time, which means that in the long run, when n gets really big and you keep getting back less and less by raising it to that power, you're getting very, very close to 0. All right, for example 3, suppose that our expressions have n's in multiple places. And it can look a little bit confusing. And we take the idea of plugging in really, really large numbers in for all the different n's. It could be a bit much to process. Okay, so to deal with problems that look like this, what we can do is focus our attention on the strongest terms. Just take the top here. You've got an n squared plus 1, okay? As n gets bigger, that plus 1 doesn't get any bigger, okay? So suppose you have a small n like 10, we'll just call it 10. Okay, 10 squared is 100, but you get 101 because you got that plus 1. Yet, if n itself is 100, you're going to get 10,000 plus 1, okay? So this term is going to continue to get bigger and bigger. The plus 1, though it's there, doesn't really do anything. Not in the long term. It doesn't make a big difference in the long term. Even in the bottom here, you've got two terms that involve n's, but one of them is more powerful than the other, and that's this one. The 2n squared, not because of the 2, that has nothing to do with it. It's because of the n squared. As you put in bigger and bigger numbers, this part is going to increase faster than this piece will. So even though you've got an n here, and the 3 is going to get multiplied by the n, where the 1 didn't get multiplied by anything, in the long run, this is going to increase in its size a lot faster than that would be. Again, take, for example, 100. If you put in 100 here, you're going to get 10,000, so it's 20,000. You put 100 here, you get 300. That it really isn't that big compared to the 20,000. Okay, so what we do here is look at each part of the fraction, and we eliminate the non-leading terms, the things that are really not powerful. Like in the top, that would be the 1. You take it out. In the bottom, you can take out the minus 3n. And we just look at the leading terms, and we do a comparison of those two. The top is n squared, the bottom is 2n squared. And if you just look at these two terms together, they sort of increase at the same rate, except that you have this extra factor of a 2. Really what you can do here is just reduce it like any other fraction. You can take that n squared and that n squared and cancel them. And it reduces down to 1/2. All right, for the other, what we're going to do is take out non-leading terms. In the bottom, that is definitely going to be the 7. Okay, for the top, you do have a square root. You've also got an n squared. The n squared is going to be the more powerful term. This is actually going to reduce the size of the number that's inside of it. It does not make it larger. Okay, that is not a leading term. In fact, the exponent that would relate to a square root is a 1/2. That would be n to the 1/2 power. And to the second power is going to be greater than the 1/2 power. Okay, so we can eliminate that one. We take the terms that we have left over. You've got 5n squared over 3n cubed. You can reduce it by taking out a couple of n's, but that leaves you with 5 over 3n. So if we just look at that part, as n gets bigger, the denominator is going to get bigger, but the numerator is not, which means that this is going to tend towards 0. Not every infinite sequence has a limit. They don't all have to have a limit. For example, the sequence that we have here, which is generated with this rule, produces this sequence. Okay, we're not going to type it in the calculator and create it. What we can actually do is just observe the first 4 terms and get an idea what's really happening here. We've got 1/2, which switches to a negative 2/3, switches to a positive 3/4, to a negative 4/5. Okay, so we're alternating between positive and negative. In addition to that, the numerator is increasing, and so is the denominator. They're both increasing. You can even describe it this way. The top is 1 less than the bottom. Okay, but regardless, let's go ahead and graph it and see what happens, because this is not going to have a limit. It's not going to have one. All right, for my graph, I went ahead and marked this off at 1 and this at -1. All right, so for our first term, we get 1/2, which is about here. For our second term, we're going to be in the negatives, negative 2/3. That would be here. All right, our third term is at 3/4. That is going to be halfway between here and there, so it's about that spot. All right, and then negative 4/5 here is going to be past that one. That would be 0.66. This is going to be like a 0.8. So it's a little bit further down, getting close to -1. We get out to that point. Okay, now if we continue the pattern, the next term is going to be 5, 6. It's going to be 5, 6, which that one's easy enough to graph. Will be right there, right in the middle of that box. After that, we're going to get negative 6/7, which is going to be getting us closer to -1, but not quite there. A little bit closer than what we have in that spot. Okay, so if we continue this on forever, what we're going to notice is that half of the points seem to be moving towards the 1. They seem to be getting close to that. But you can't discount what the other dots are doing. They're getting closer to -1. Okay, so we have a situation here that the limit tends towards 2 things. It tends towards 1 and -1. It goes to 2 different places. It just alternates back and forth between them. If you have something like that, it would be an example of when the limit does not exist. And last, we do have sequences that go to some place, but not necessarily a particular value. Example 5. We have an arithmetic sequence here where all the terms are increasing by 4. You go up by 4, up by 4, up by 4, and continues on. So if you were to plot a graph of this, you would just see dots increasing in their height by 4 every time. In this case, it is going somewhere. It's not going to like 2 different places or nowhere, but it isn't going to a particular value. This limit is constantly increasing without bounds. So it tends towards infinity. You can have that as an answer. It's an infinite limit. If the value of each term just continues to increase upward, then it goes to infinity. Okay, example 6. For this sequence, you're going to notice that they're all negatives. We start at -10, we go to -100, -1000. We probably get the idea from there. These numbers are getting bigger, but they're getting bigger in a negative direction. This limit decreases without bound, so it tends towards negative infinity. If you have a sequence that's constantly decreasing, below 0, not going down to 0, but constantly decreasing lower and lower and lower, we say that it is going to negative infinity.
Later, blah.